Here we have page 392, number 23. We have borders identified as y equals x squared, which I've gone ahead and graphed in advance, and y equals x plus 3, which is the linear equation represented right here. Our border, or our axis of revolution for all the first few problems is the x-axis. So this is our question. We could use the picture to decide on dx or dy, and we could use the picture to decide on circle, disk, or washer. However, I think it's an important skill to be able to read the equations, read the descriptions, and make the right determination, because there's some pretty simple clues. We know that this is a dx problem because our axis of revolution is a horizontal line. If it was a dy problem, this would be a vertical line, and vice versa. We also know that washer is going to be the geometric shape of our slice, because the x-axis, which can be rewritten as y equals 0, this is neither of the borders for our function. If the border is the same as the axis, it would be a circle. In this case, our borders and our axes are different, so this is what creates the washer. The other key thing we need to identify in a washer problem is the outer function and the inner function. Our axis of revolution is right here. And if we are looking at the region that's enclosed or bounded by these curves, it should be clear to us that x squared plus 1 is closer to the line, so we dub it our inner function. The linear equation, for the region in question, the linear equation is farther away. So for the region, that linear equation is our outer layer. These are going to be key words in helping find big radius and little radius. We've identified dx and we've identified washer by just focusing on how the problem is described. And then with a little common sense graphing, we recognize which function is farther away or is outer, which function is closer or inner. We are ready to slice, and our slices have an area based on the area of a washer formula. Just pi big R squared minus little r squared. We are ready to approximate. By the way, if you find these steps fast and you haven't looked at 21 or 22, I do go through them in a little more detail in those steps. This is the quicker version, assuming you've watched those videos. So for approximate, we can always approximate big R of x by focusing on outer minus axis. In this particular case, our outer function is the linear equation x plus 3. And our axis is the horizontal line of the constant function, 0, giving us x plus 3 as our big R of x. Little r of x has a similar procedure. Little r of x is inner minus axis. Based on our visual, inner or closer to the axis of revolution is our quadratic equation, x squared plus 1. And our axis of revolution is still the constant function 0, giving us x squared plus 1 as our little r of x. Now that we've identified big R of x, and we've identified little r of x, we can go back and rewrite our area using x as the primary variable, or the only variable. The area as a function of x is pi big R squared. It is very important to use parentheses so that we combine only like terms and we simplify properly. Little r of x is x plus 1 squared. For the moment, we're not going to simplify this. On the next screen, we'll do some simplification. We'll work out antiderivatives by hand. But let's focus on just doing good setup for this screen. One extra challenge in this problem that is not in the first two problems is determining the A value that represents the start of the region and determining the B value that represents the end of the region. Fortunately, it's a pretty basic algebraic process. We have our function, and we have our function. Setting them equal will determine when they intersect, and that will determine our values for A and B. If we move these two terms with subtraction, we get a quadratic equation. And we get a quadratic equation that factors in a pretty friendly and easy format. According to this, one intersection is x plus 2, and that seems to be pretty accurate on our graph. And the other intersection is x minus 1, and that also seems pretty close to what we've sketched out. So we've identified our A and B values. So we have all the ingredients necessary to write our volume. The integral from -1 to 2, pi x plus 3 squared minus x plus 1 squared dx. On the next screen, I'm going to go through and simplify this. However, it was not required for this question. 21 and 22 were about the difficulty level that usually you need to be able to work out by hand. This is certainly doable by hand, but when I look at it, I would guess that this is more likely to appear in the calculator section. But I can't promise that. This can be done by hand. And it's not difficult, it just requires a lot of steps. Let's go back to that area formula. And before we plug it into the integral, come up with a slightly simpler representation. We should probably go ahead and expand these two binomials. The first binomial expands to x squared plus 6x plus 9. And then it is very important to keep some parentheses so that you properly subtract this term. X squared squared is actually going to be x to the 4th. And then 2x squared. And then the final term is plus 1. Because we've kept our parentheses, when we combine like terms and we simplify, we'll be able to properly subtract each term and not combine things in an improper manner. I like to write things so that the positive terms are first. So I do see that 6x is a positive term with no other like terms. We do see that 9 minus positive 1 should be a positive term. And then we have our negative terms, an x squared minus a 2x squared, and a x to the 4th, which is negative. We don't have any like terms. We've expanded and combined like terms. So we're ready to go back to that integral. The volume is the integral from -1 to 2 of pi 6x plus 8 minus x squared minus x to the 4th dx. You may have the urge to distribute this pi. I wouldn't do that. That's going to make life harder. What would make life easier is actually to factor out pi fact, in order to save space, let's just take pi, which is being multiplied by the entire function, and rewrite it outside of the interval. The reason that's to our advantage is we have a pretty long function, but not a difficult function. The operations that connect each term are just simple addition and subtraction. So that means we can focus on the antiderivative plus the antiderivative minus the antiderivative minus the antiderivative. So 6x squared over 2 plus 8x minus x cubed over 3 minus x to the 5th over 5. We have our values of A and we have our values of B. At this point, we simply want to find g of B minus g of A and multiply the final result by pi. I do recognize that I'm running out of space, and I want to get as many problems done as possible today. So let's just go back to this by hand procedure and recognize the antiderivative is doable. First, you need to simplify that area formula. The antiderivative is doable. The key ingredient was taking that area formula and using good algebra to simplify it and factor out that pi. If you have pi in here, then you're going to have a bunch of pi in your antiderivative too. Probably best just to save that for the end. Give me one moment. If you did work it out with a calculator, which, although I did not intend to, I decided to go ahead and do to save the time, what you should have arrived at was approximately 73.513. And because I was too lazy to finish, frowny face with a mustache and ears and eyelashes. DSA.